All right, so chapter 2 dealt with really significant digits, international system of units like your meters versus your kilometers, unit conversions, which I don't really have a lot of testing specifically. My plan was not really to test your conversion ability because that's going to be built into the rest of the test. When we start doing acceleration and things like that, you're going to naturally have to do conversions. So I'm not going to force you to do separate conversions here, because I do make you do conversions throughout the test when you need to. So I'd rather you just recognize when you need to do conversions versus memorize a whole bunch of random conversions that honestly, unless you use them regularly, you're just going to look them up, right? So there's no need to memorize a ton of conversions. But I do want you to know how to do it because you do have to do conversions throughout the test sporadically, depending on what I've given you. Be able to explain and use these principles, like, time and, all those different measurements. There's 3 of them. Fundamental, standard notation. I just want you to understand what that means. Unit conversions, errors, absolute error, percentage errors. Again, I want you to understand the terms. But what I've mostly tested you on in being able to do it are your significant digits. So I'm really just looking for, do you understand how to determine how many significant digits you have? Just as a reminder, you can do all of your rules like zeros before the decimal, zeros after the decimal, in between 2 significant digits, all that good stuff. Or really, you could just write it in scientific notation. When you write it in scientific notation, the number of digits that you have left is your significant digits. So if I were to write this in scientific notation, I would want it to be between 1 and 10 to my number, which is less than 10. So that means I'm going to put that decimal right here. So I'm going to move that decimal over. So I'm going to write that as 3.05. Moved it over 3 places, right? How many digits do I have there in that number? Well, I have 3. That is 3 significant digits, right? And so that's the fastest way to tell how many significant digits I have. Then we had some rules. When you are multiplying, using significant digits, remember you're going to use your least number of significant digits. That is multiplying. So when I look at these and I multiply them, this guy has 5 significant digits. This guy has 2 significant digits. So when I multiply, I am going to get this big number here. However, I only had 2 there, so I'm going to say something like that for significant digits, all right? Adding is a little bit different. When you're adding, you're actually talking about precision, not significant digits. So it's a little bit different when you're adding. When you're adding, they want to know the least precise of them. So this does have 2 significant digits. This does have 4 significant digits. Your brain may say, oh, I'm adding, so I need 2 significant digits, but that's actually not the case. The least precise of these is my 3.2. 3.2 is my least precise, meaning they only gave me 1 decimal place. This is more precise. They had to have a tool that measured to the 100th of a place right there. And so I'm going to use my least precise measure. My least precise was 1 decimal place. So when I add these two, I do get 15.57. However, I'm going to use 1 decimal place here because that is the least precise measurement that I had. So I am going to say 15.6 grams there. Least precise when it's adding and subtracting. You are using least precise, not your significant digits per se when you're adding and subtracting. Least precise. All right, you do need to know all the terms. These are straightforward. They would have been from your handout. Explaining and understanding distance versus displacement, speed versus velocity. Remember, speed does not have direction, velocity does. Scalar versus vector, remember if it has 2 dimensions, it's going to be a vector. So the one above it is an example of scalar versus vector. Average speed, instantaneous speed, just understanding that we are comparing over a distance versus a speed at a specific spot. Positive or negative velocity or acceleration, understand velocity has direction, so positive velocity depends on which direction you're going, negative velocity, other direction, acceleration, speeding up versus slowing down, slope of the tangent line versus area under the curve, position, time, velocity graph. All I'm trying to make you understand is that when you are looking at your placement to your velocity, that's the slope there. If you're looking at velocity to acceleration, that's your slope. And if you go the other direction from acceleration to velocity, then you start talking about area. So those are just concepts that we did when we did some graphing with our handouts. Free fall motion, remember with free fall, you know your acceleration, it is gravity, right? And so we are going to have some where, again, you're going to be able to use your formula sheet, which you're going to be able to use it when you're practicing. But remember, if you have no initial velocity, you're going to zero that out. If you have acceleration and the only acceleration you have is gravity, that is your acceleration. So you're going to have to think about that with some of these. All right, so examples of what we did in this section. First set of examples, pretty straightforward. Sarah swims 50 meters east in a pool, then turns around and swims 30 meters west. What is her displacement from her starting point, and at which distance did she swim? Remember, displacement is how far away I am from where I started. All right, so you want to use kind of conceptually what it tells you. If it says east, you're going to think of that as just the movement. So if she's starting here and she went 50 meters, then she turned around and she went 30 meters. My displacement is just how far she is from where she started. So that I'm just going to subtract those two. My displacement is just going to be 20 meters. All right, but distance is different. Distance is how far did she actually swim? Well, we're actually going to add that up because she swam 50 and then another 30. So overall, she swam a total of 80 meters. So I'm just trying to make you remember distance versus displacement. All right. There are going to be times when you might need to sketch it because it may not do just east and west. It may say west, then north, then east, all right? And so you may need to triangulate it with like Pythagorean theorem as well. But I have every confidence that y'all can do Pythagorean theorem as well. All right, we also did acceleration and deceleration. And so we had problems like number 2 here, a passenger train's approaching a station at 144 kilometers per hour. He applies the brakes, causing the train to decelerate uniformly at 2 meters per second. How far does the train travel before coming to a complete stop? Again, I'm going to let you use your formula sheets, but a couple things is if you don't have the time, which in this case they didn't give us the time, we're going to use one of our formulas where we're just saying my final velocity squared minus my initial velocity squared over 2 times my acceleration. Again, one that we're going to be able to have. So in this case, it says a couple keywords. The station starts there. That is my initial velocity, 144 kilometers per hour. Final velocity, well, coming to a complete stop. That is 0 kilometers per hour. Acceleration, decelerate, I'm going to note that with a negative. So just like I said at the beginning, I'm not going to test you on just straight conversions, but clearly I have a conversion issue here, right? We have kilometers per hour and meters per second squared. And so we do want to convert this kilometers per hour to meters per second, right? And so you do want to do your conversion there. before you plug anything in. All right. So before you plug anything in, you want to do that conversion. And then using that formula, we're going to say my final is going to be 0. My initial, I'm going to use that 40 meters per second over 2 times my acceleration, which is a negative 2 meters per second squared. How many significant digits do I want here? So I'm going to want 3 significant digits. You end up with a nice, round, beautiful 400. How do I indicate where my significant digits stop? Yeah, I can decimal or I can underline it if I want to, yeah. And that is meters. I converted to meters per second. My distance is what I'm looking for, so my distance should be in meters there. Sarah is visiting the Grand Canyon, decides to conduct a science experiment. She drops a small pebble from the edge of a cliff that's 120 meters high. Assuming no air resistance, how long will it take for the pebble to hit the ground below? What's the only thing affecting the pebble if she just drops it? Gravity. So my distance traveled, dropping, we're going to say 120. It's just this one that I feel like we've used a million times. Right? So multiply by 2, divide by negative 9.81, and take the square root. So it should have taken 3 significant digits would be 4.95 seconds. Chapter 4. Again, these should all be on your handouts, but you have your terms that you need to know. Examples of vectors and scalars, again, as mentioned in this chapter, vector notation, labeling it. We also did our mapping, Cartesian, which is your coordinate plane, your cardinal, which is like north of west, and your map, which is like your true north or your bearings. Calculate sides of the triangle with right angle trigonometry, Pythagorean theorem. You're really going to use this more in the process. I'm not going to give you just sample problems of calculating those. Sketch vector addition. The only reason you're going to have to sketch it really is when we start doing the word problems, and you're going to want to be able to sketch what they've given you to be able to get an idea of what you're doing and which quadrant you're in, and then solve your word problems algebra. First of all, do you remember your Cartesian, cardinal, and map directions? Remember when it gives you a T, that means from true north? It could also give it to you in bearing form, like 0, 6, 0 is the same concept. And so this is a map direction, meaning I start at the top and rotate clockwise. Cartesian is going to be start at x-axis and rotate counterclockwise. And then cardinal is just going to give you the directions, like 35 degrees east of north, something like that. All right. So this particular one is a map, which means I'm going to start at my north and go clockwise. That first 90 hits right there at the axis, so I've gone another 15 degrees. So I'm going to say this is a map instructions, and my reference angle is closest to the x-axis would be 15 degrees. So that's what you're going to use in these word problems. Remember, these word problems give you 2 things that are affecting it. And you're going to set up my initial, you're going to add whatever is affecting it, you're going to use your magnitude equation to calculate that, and you're going to use your inverse tangent to calculate your direction. And so this is the only time I would say you would want to know how to sketch. So if I'm doing this, I'm going to kind of sketch my initial, I'm going to sketch anything that is affecting that, and then I may actually need to go back and get an idea of where I am finally, right? And so when I'm sketching these, I'm going to look at my first movement there that it talks about. It says an airplane is scheduled to fly 300 kilometers per hour at a bearing of 062 degrees. All right. So that bearing tells me that I am 62 degrees from north clockwise. So that means this guy is 62 degrees. But remember, your calculator always assumes a reference angle. So when you plug these into your calculator, it is going to do reference angle there. So you need to use reference angle, which means I will get that by subtracting that 62 degrees from 90. So the angle that I'm going to use in my calculator there is 28 degrees. Because they've given me a bearing, my calculator assumes reference from the x-axis, all right? Remember, I'm going to break these down into different components. So I'm going to break them down into an x component and a y component. I'm going to do that using the magnitude of that guy. In this case, the magnitude of this is 300 kilometers per hour. Everything they gave me was kilometers per hour. You do not need to do any conversions on this one. It's not asking for acceleration. Everything is in kilometers per hour. If it had given me seconds for something or something that made me think I need to convert, I would, but don't automatically convert just because you see kilometers per hour, okay? Check your problem. So I'm gonna actually leave my kilometers per hour alone. I'm gonna break this down by saying my 300 kilometers per hour times the cosine of the 28 is going to be the x component. 300 kilometers per hour times the sine of 28 is going to be my y component. And I'm going to break it down into an xy. So the velocity here is 264, and I'm not going to use significant digits right there. I'm just going to be a little more precise when I do this. I'll worry about significant digits at the end, but I'm going to break that down into components. Positive x, positive y component. That is the first thing that is affecting this particular airplane. It is kilometer, it's bearing. The next sentence tells me that something else is also affecting it. The weather forecast predicts a steady wind from the southeast. Remember those directionals that combine two is always a 45-degree angle. You just have to figure out where he is. So southeast is exactly what it sounds like, south and east. However, this particular one said from the southeast. That's vitally important because southeast is right here. But if it is moving from the southeast, it is actually going to jump and cut across that way. From the southeast is actually 45 right here. All right, so when you see the word from, it's actually going to shift both of those. Northwest, if it is from southeast, then it is moving northwest. Does everybody understand that? From the south means it's moving north. All right, from the northwest means it's moving southeast. Okay, so it's moving exactly opposite when it's coming from that direction. So my reference angle again here is going to be that 45. However, when I do this calculation, it is going to be a negative x and a positive y. How do I know that? The quadrant that I'm in, all right? So we're going to still take the speed of that guy, which is 85 kilometers per hour. We're going to say cosine of 45. It's actually going to equal the same thing as the sine of 45. They have the same sine and cosine. All right? But when I do this, I want to write down a negative x value and a positive y value because I'm combining these two. I'm going to add these two to get my movement that's actually happening to this plane. And so I'm just going to add them. I'm going to add my x values. My x values are 264.88 and negative 60.1. My new x value over here is going to be 204.78. I'm going to add my y values. That's going to give me 200.94. That is my horizontal breakdown and vertical. If I need to calculate then my magnitude, this is Pythagorean theorem, remember? My magnitude is going to be the square root of my x squared plus my y squared. So you need to do that with your x's and y's. So the magnitude, how fast this guy is actually going, you get 286.90, but yes, we need significant digits, specifically 3 significant digits, 287 kilometers per hour. It's also asking for direction. Remember, direction uses my inverse tangent. So for direction, inverse tangent, make sure it is y over x. You can completely ignore your positives and negatives here because it is going to do a reference angle. So to give a bearing, we're going to have to back into it anyway. So when you do the inverse tangent here, you get, with 3 significant digits, 44.5 degrees. However, remember, and this is where I said you may want to draw it one more time to get an idea of what you're talking about. This has given me the angle from my x-axis up. So when I put that in my calculator is going to give me this angle. Everything it's given to me has been in a bearing, which means I need to subtract that back out, right? I need to say 90 minus that 44.5, which is 45.5 degrees. To indicate that you have a bearing or a true north position, you can put that T. Had it been, I guess you could say 046, 045.5, but typically you can just put the T, or you can write a bearing of 45.5 degrees. But you do need to do it from true north, and it has given it to you from the x-axis when you put it into your calculator. We have our terms: correcting for wind and current when navigating. Frame of reference does not affect displacement of the object. Difference between horizontal projection versus projection and angle. Remember, horizontal does not have any vertical velocity. The only thing affecting a horizontal projection is the initial horizontal velocity and gravity. The difference between x direction and y direction functions. So meaning you have to understand if it says like parallel or if it gives you an angle, that you have different movements based on what that problem has given you. What affects time of flight and why? Remember, time of flight is affected by initial vertical velocity, height, and our initial height and gravity, right? So you have to consider that it is gravity pulling down on this, right? Your horizontal velocity doesn't actually affect time of flight, just your vertical velocity and your height, because gravity is the only thing pulling down. Maximum range of a launch angle and y. So remember, maximum range is 45 degrees. It's going to be moving the same horizontally and vertically when you have a 45-degree angle, because that's when you have the same sine and cosine. So some example problems correcting. I will admit this is kind of a stronger correcting one than we've done in the past, but that's okay. So a medical evacuation helicopter needs to fly from a hospital to an accident site 100 kilometers away. Bearing of 30 degrees. That is a true bearing from north. If the airspeed is 200 kilometers per hour and there's a wind blowing from 120 degrees at 40 kilometers per hour, what bearing should the pilot use to reach the accident site? All right, so you're going to think about this kind of the same way we did the other problem that we just finished. What is he initially doing? More like, what does he want to do? What is the wind doing to it? And we're actually going to do the opposite here. So if the wind is blowing me west, then I want to move east, right? And if the wind is blowing me north, then I want to move south. You kind of want to think that. So for these problems, when you're correcting, remember you're doing the opposite. All right? So I'm going to do exactly the same thing here. My bearing is 30 degrees, which means in my calculator, I'm going to use what? If that's 30 degrees, what am I going to use in my calculator? I'm going to use 60 degrees. So we're going to use 200 times the cosine of 60, 200 times the sine of 60 to get my initial vertical and horizontal breakdown there. This other one's a little bit different. It is asking for a wind. However, it gave me 120 degrees, which is right here. All right. 30 being my reference, but it did say from. Remember what I said about from? It's going to slide it right across that origin. And so if I'm going to use from 120, It's actually going to look like this, right? From 120. So I am going to use that 30 degrees, but my X's and Y's, that's how it's actually pushing me. It's going to be pushing me west and north, okay? And so when I put these into my calculator, I'm still going to use the 30, but I'm going to say cosine, let's see, we have to use our 40 kilometers per hour, cosine of 30, 40 kilometer per hour, sine of 30. So it is pushing me west and north. It's pushing me west and north. Everybody see that? Pushing me west and north. So in this case, how do I want to overcorrect? Well, I want to correct by moving east that much and south that much. I am correcting. So remember, when we correct, we want to do the opposite of what it's doing. We want to do the opposite of what it is doing to us here. All right, so now I'm ready to add these because I'm correcting the opposite direction, right? So while it is pushing me one way, I'm going to correct it by going the other way, right? And so you're going to do exactly the same thing. It wants a bearing. So you're going to add those across now that I've corrected the opposite direction, and then I'm just going to get my inverse tangent. So when I correct, just adding those together, and I'm going to use my inverse tangent. I will say again that it is going to give you your reference angle. So if you're going to give it to me as a bearing or a true, you're going to subtract from 90 degrees to get that true. But the difference between this is they're asking what bearing should he use versus what is its actual movement. So the difference between this question and the question that we did in the chapter before is, the chapter before it just said, hey, including the wind, what is his new bearing and magnitude or new velocity, right? But this one is saying, hey, because of the wind, how should he actually direct it so that he's doing what he wants to be doing? So those are the difference in these two. They feel the same, except one, you just straight up add them and say what new is happening. The other one, you're doing the opposite. So Formula One race car accelerates from 108 kilometers heading east to 252 kilometers heading northeast. So we're going to start with our ending here because acceleration is just velocity over time, right? So we're going to say, well, the initial heading was 108 east, but we're going to take our ending, which is the 252 northeast. That's a 45-degree angle. We're going to subtract where I started, which was just 108 east. So X movement, no Y movement there. When you subtract in starting from ending, you get that. Because it wants its acceleration, we have to first calculate velocity, which is my magnitude. So you're going to do your x squared plus y squared to get my magnitude. 191.5 kilometers per hour. Acceleration is in what? Meters per second squared. So I naturally have to do a conversion here, right? So my conversion, remember, 1 kilometer per hour is the same thing as 1,000 meters per 3,600 seconds. That is my velocity. Velocity divided by time. What was my time here? 6 seconds. So velocity divided by time will give me my acceleration. If an arrow is shot at 62 degrees to the horizontal with an initial speed of 40 meters per second, what is its range? If they do not give you an initial height, you're going to assume ground level. Or at least, in this case, you can assume that where he shot is the same distance as the target, potentially. I don't know what, but they didn't give me an initial height, so we're going to assume ground to ground. All right? Remember, because they're asking for range, I'm going to need both my initial vertical and my initial horizontal velocity. Initial vertical velocity is going to give me what time, how long it was in the air, and then I'm going to take that and multiply it by my horizontal velocity to figure out how far it went horizontally, right? So I'm going to use my sine and cosine here. Remember, my initial velocity for horizontal is going to be that initial velocity of 40 meters per second multiplied by the cosine of the initial angle that it gave me. My initial y velocity is going to be the same thing, but I am going to use my sine. If you're trying to figure out when it hit the ground, your final position is going to be 0. So you end up with that quadratic every single time. You end up with the 1/2 gravity times squared. So you end up with that negative 4.905 times squared. Plus your initial vertical velocity. And you want to know when it hits the ground. If I had had an initial height, I would have added that there. When I have an initial height, I need to use the quadratic formula. When I don't have an initial height, you can just factor out your time. One of the times is going to be 0 when you started. The other time is going to be when it made it across and hit the ground. So when you factor out your time, clearly you're going to start at ground level. And you have something that looks like this. Set each one equal to 0 and solve. Obviously, we know the first initial 0. So you end up with 35.3 divided by the 4.905. Your time was a total of 7.197 seconds. I'll get to significant digits at the end. That's how long it was in the air. So then to figure out how far it went, we have to multiply my initial horizontal velocity multiplied by my time is going to tell me how far it went in the horizontal direction. So I'm going to take that 18.8. I'm going to multiply it by the total time it was in the air. I'm going to round it to, this is 2 significant digits. So I get 135 meters, 2 significant digits would be something like that.